In this video, we're going to learn how you can take some data that's not linear. For example, it could be data that's parabolic, data that's in a square root graph, certain sets of nonlinear data, and how you can force them into a linear shape. So you have a two-dimensional graph and a line on the graph that's really easy for you to find an equation for. That's what linearization of nonlinear data is. I was going to mention there are only certain types of data sets that this works for. We're going to learn what those data sets are, and we're going to mention as well, we're going to encounter these data sets throughout the year in physics. Data sets that are not linear but are linearizable. We can make them into linear distributions. And why would we do this? Well, linearization helps us to visualize complicated data sets. It's pretty tough for you to visualize what's happening in a square root graph. Sometimes. Sometimes it's not so bad, but sometimes it's a little difficult for you to visualize what the graph even means. But linear graphs are very easy to visualize. So linearization is going to help us visualize complex data, and you could draw a line of best fit for the data by hand when it's linearized. You can't really do that with parabolas and square root graphs and inverse graphs. If you've ever tried to draw a parabola of best fit, you'll realize it's a very mathematical process to do so, and that's much better left up to a calculator or a computer. The same with a square root of best fit. But lines of best fit are easy. You just make sure that there are as many data points above the line as there are below the line. You make sure that they're pretty evenly spread away from where you draw the line. And then once you have a line of best fit drawn, you can find the equation using slope-intercept form very easily as well. So this is just a way to make data more accessible to us and easier to work with. The general equation for a line you're used to seeing is probably the slope-intercept form of that equation, y equals mx plus b, and you're used to seeing these descriptions of this equation. M is the slope, b is the y-intercept, and the other two values are variables that make it graphable on an xy coordinate plane. Well, we're going to go a little bit deeper than just this as we work to understand what this equation is actually telling us. We really have to understand the slope-intercept form of the equation to make linearization happen in a way that we can make sense of it. Let's dive in deeper to the slope-intercept form of this equation and really understand what this equation is telling us. Because really this equation is telling us some important things about lines on graphs and what they actually mean. What's actually happening here? So I'm going to add a few more labels to this equation other than just the slope and the y-intercept. First of all, it's important to note that y and x are meaningful. Usually we just add this into slope-intercept form because that's what allows us to graph it as a line. But those variables actually have meaning. Y is the dependent variable. X is the independent variable. Now let's just talk about what the word variable means. In our equation, a variable is a quantity in a function, okay? And remember, a function is something where you input something, some value. We're going to input some x value, and it's going to return a coordinated y value, a y value that makes sense for that x value for some reason. The variables are quantities in function that can take on a range of values. It's not just a fixed value. They can change. They can vary, right? So x and y are variables in this function. The independent variable, which is x, is a variable whose value does not depend on another variable. And it's important to note that by convention, we plot the independent variable on the x-axis of the graph. Also, just to remind you, time in a graph, if time is one of the variables, it's usually the independent variable because time flows without really depending on anything else. Other things tend to change with respect to the independent variable. And that brings us to our dependent variable. It's a variable whose value is coordinated to another variable. Now, in coordinated, do you hear that word coordinate? That's why there's a y-coordinate for that x-coordinate. First, we list the value that doesn't depend on any other number, but there is a value that depends on the independent variable value. So we have the one that doesn't depend and then the dependent one listed second, and that's how we get our coordinate pair. We plot that value on the y-axis of a graph. And then as opposed to variables in an equation, we have some constants. Constants are quantities in a function that have the same value, and they are the ones that determine how y is coordinated to x. They help us to plot the relationship between the x input and the y outputs, or the differences in values between the coordinates of the coordinate pair. Okay, so there are some constants in this equation. For example, slope is a constant. It's the constant rate of change between x and y. So another way to think about it, m is the value, and if you want to think about it, it can be any fractional value. When we calculate m, it's the rise over run fraction, right? But it's a value that we multiply by the independent variable that will output our dependent variable in a line. And because it's a constant value, our line is going to increase in a very constant way or decrease in a very constant way as we graph it. And then b is the initial value of the dependent variable. And anytime you have an initial value, that's also a constant, because what the value started as isn't going to change as our independent variable changes. So our dependent variable is just this constant value. So you see that this equation is actually just a mix of variables and constants that tell us a very specific thing about our relationship between x and y. Some other things to note, x and y are always measured using some kind of units. In math class, you don't worry about this because you're just visualizing the relationships between variables. But in physics, it matters what the units are. So we're always going to list the units. Interestingly, b, the initial value of y, has to be measured in the same units as y. It wouldn't make sense if it was different units because it's an initial value for our y. So it has to be the same. And then lastly, the units of m are the same as the units of y divided by the units of x. So that helps us again make sense of what rise over run is. It's just giving us the relationship of how y changes with respect to x, and it can all be summed up in one constant value on a line. Lines make intuitive sense. When you think about data and you can visualize it on a linear graph, oftentimes you don't really have to think about all of this and what's happening on that linear graph. It just makes sense to your brain how these two-dimensional plots that come out linear actually work and what the relationships are. But now that we're going to be forcing higher order data sets into linear data sets, it's going to be important for you to really understand what's happening in a line as I've showed you here. There's one special line that it's worth talking about because this line comes up again and again in linearization problems. And that line is the line that passes through 0, 0 on a graph that has a 0 value for its y-intercept. Whenever we choose reference values when we start graphing data, it's helpful for us to choose reference values that puts our initial value on the x dimension. In this case, this graph is a position time graph. So we could choose that our initial time, our starting time, is 0 seconds. For any independent variable, when you graph it out, you're probably going to choose 0 as the initial value and then start counting up by a set interval on that axis after that. And the same is true for the y-axis. In this case, my initial position is 0 as well. But remember, we're not necessarily talking about position. It's just whatever gets graphed as the dependent variable on your y-axis. As long as the initial value of that is 0, we call that line that crosses through the point 0, 0 proportional. And proportional relationships are very common. I just want to mention this. You are never allowed to assume that a set of data that you've graphed is going to be proportional. So you shouldn't force your lines of best fit to go through 0, 0. Your line of best fit is going to cross the y-axis wherever it has to make a line of best fit. So I just want to mention that because I know that a lot of programs that allow you to calculate linear regression lines do allow you to choose to force the point through 0, 0. You should never choose to do that. Instead, you should verify that the graph's y-intercept is close to 0 if you expect it to be 0. And we'll talk about that as we go through this as well. All right, so let's just consider our general y equals mx plus b equation once again as we look at some actual nonlinear data, and we're going to manipulate our nonlinear data to make it linear. How are we going to do that? Well, here's an example of a nonlinear distribution. This is a parabola, okay? And I'm going to take my general equation for a linear function, and we're going to compare it directly to an equation for a parabola. In this case, it's the actual equation that I'm using to explain a set of data that I've collected. And I can see that this is a kinematics equation. 1/2 at squared is a position equation that explains the position when there's a constant acceleration. I'm also noting that this is 1/2 at squared. In this kinematics equation, there's also supposed to be an initial velocity term and an initial distance term. Those terms must be 0. So this object is starting at rest and then accelerating at a constant rate. Now what we're going to do is figure out the relationship between these two equations. Okay, the linear equation that we're going to be using to linearize this nonlinear equation. And what we're going to be looking for is a one-to-one correspondence between the values that we said are generally in the slope-intercept form, dependent variable, independent variable, slope, and possibly a y-intercept. And we're going to be looking for a one-to-one correspondence between those values and values that are in the actual equation on my graph. Okay, in this case, we're going to be graphing x position with constant acceleration. Now, do I have a dependent variable in both of these? Yes. My y value in the slope-intercept form, and unfortunately, it may be confusing because this is a horizontal acceleration variable, but x is on the y-axis. X is being distributed on the y-axis here. So that's going to be my independent variable. I've coordinated that my x value is directly just going to be my y value in the slope-intercept form of the equation. So when I graph a linearized version of x equals 1/2 at squared, I'm going to be using my x position values as the y values, y coordinates in y equals mx plus b. Next, the slope has to be constant, okay? So I'm only able to circle values that are constant here. 1/2 is a constant, and I said that this is with constant acceleration, so a has to be a constant as well. Now, constant doesn't necessarily mean that I know the value. I don't know what the value of acceleration is here yet, and I'm actually going to be using this to calculate what the value of acceleration is. But that doesn't mean that it's changing just because it's unknown. So a is a constant acceleration. I'm allowed to do that. And then lastly, my independent variable is going to be the time value. But here's what I'm going to do. Instead of just coordinating x in y equals mx plus b with a variable to the first power, I'm going to coordinate it to a variable raised to the second power. And this is the actual linearization step that's going to take my nonlinear plot and turn it into a linear distribution. Now, before we move on, let's just note a few things. First of all, I'm going to note that my slope is being coordinated to 1/2 a. So whatever I calculate as a slope value from my linear regression, it's actually going to be 1/2 of the acceleration. And I get that directly by looking at how my general equation relates to my actual equation. I'm always going to note what the slope value calculates to. I'm also going to note that if I were to look at a real data set here, so here are my times for a real data set. This data set was collected from time 0 to time 3 seconds. Here are my x positions. Notice that in many cases, in this case, I don't have an initial y dependent variable value. Now, if you look at my data set, yeah, it's 0.01, but that's really, really close to 0. This is really close to running through 0, 0. So I'm going to treat this as if it does. And I'm going to get rid of the b in y equals mx plus b. You'll notice that there was nothing that b coordinated with in the actual equation anyway, and that happens all the time. That just means that I was good at setting up my reference point so that I didn't have an extra consideration in the equation. So it starts at 0, 0. But now, how do I actually linearize this parabola? This is clearly a constant acceleration distribution for position over time. Well, here's what I'm going to do. Instead of graphing the x position against time, I'm going to graph the x position against time squared. And what's that going to do on my x-axis? Well, I'm going to need a larger distribution of values. It's going to need to go up to about 9 instead of 3. Well, that makes sense because I'm squaring 3, right? I'm not going to change the way that the axis is laid out, though. It's still going to count up by 1 unit per tick mark. But what I am going to do is, by graphing my x position versus time squared, I'm going to spread out the coordinate pairs so that my x coordinate pair is going to have a larger spread the farther I go on the graph. And what that's going to do is it's going to change the distribution of the y values, so now they're linear. Now I've linearized this data set by, instead of graphing t against x, I graph t squared on my x-axis. And notice that now this makes a pretty good linear shape. I've done my linear regression on this using Excel, so I know that my y value, which in this case is x position, equals 0.7499x, and then there's that extra term at the end. Let's go ahead and plug this into my slope equation. The slope is 0.7499, and I know that equals 1/2 a. Solve for a, multiply both sides by 2, and then we find that our acceleration is 1.5 meters per second squared. So this was an effective way to figure out what the acceleration was in this data set. Now notice that there is a y-intercept, and I thought there wasn't going to be a y-intercept, but when I ran the linear regression, it was there, and I can't just say that it doesn't count without proving that it's small enough for me to not have to worry about. And here's how we're going to prove that y-intercept value doesn't really matter. It's negligible. We're going to use something called the 5% rule. And that is that if the b value in your slope-intercept equation is less than 5% of the maximum y value in your data set, then it's negligible and you can exclude it. So let's just look. What's our maximum y value in our data set? Well, our y values, remember, are the x position values. And our maximum x position was 6.78. So what is 5% of 6.78? Well, I multiply that out, I find it's 0.339 meters. Is 0.0015 less than 0.339? Well, it sure is. It's quite a bit less. So because of that, that means that I can just exclude that 0.0015 from my regression equation because it's small enough to be negligible and it counts as 0. And that tells me that I have essentially a proportional relationship between y and x in my slope-intercept equation, or in this case, to be more specific, between the x position and the time squared value. All right, and that's how it's done. We've linearized our data set, and then we used it to calculate acceleration. There are certain types of data sets that this works for. And I'm going to show you the several types that we're going to run into in our physics class, but keep in mind that this is not an exhaustive list. There's others out there as well that would be linearizable. Positive quadratic and negative quadratic functions are linearizable. Okay, they're really, I could have just said quadratic, but I wanted to emphasize these separately because sometimes they look like different graphs, so we treat these different types of problems separately, and both of them can be linearized. Another type of relationship that can be linearized is a square root relationship with a graph that looks like this. Notice that in my equation, the square root has to be calculated by taking the square root of both sides. You'll either see this as a square root value on your independent variable or having a squared dependent variable as I have here. And then there's two types of inverses that look very similar. They behave the same way essentially, but I'm also going to treat these separately because they come up in different equations in physics. So we could linearize an inverse relationship or an inverse square relationship. Importantly, in order for us to linearize any of these graphs, they have to be centered on the y-axis of the graph. So that means for our quadratics, the maximum or minimum value must be on the y-axis. For a square root, it needs to emanate from the y-axis, from the point 0, 0. And for inverse and inverse square, they have to have an asymptote on the y-axis for them to be linearizable. All right, at this point, let's dive into graphing another nonlinear data set as a linear data set. And in this case, we're going to use an equation you're probably not familiar with. We're going to consider the equation for acceleration due to gravity, but at different distances from the Earth. You may know that acceleration due to gravity at Earth's surface is negative 9.8 meters per second squared. But actually, that's just an average value for what acceleration is when you're standing on the surface of the Earth. That value will be different depending on where you are standing on Earth's surface. For example, if you're up in the mountains, you're farther away from the center of the Earth, and therefore your acceleration due to gravity is going to be a tiny bit less. And the further away you move from the Earth, like if you're an astronaut and you get into a rocket ship and you blast off from the Earth and move further and further away, the pull of gravity is going to get less and less the further you get away. So it's not a linear relationship. I can't just graph that relationship on the line y equals mx plus b straight out. Instead, the relationship looks like this. The acceleration due to gravity is some constant that capital G is actually called the constant of universal gravitation, and it always has this value, 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. This value is just a fudge factor value. It's a constant that's plugged into the equation that makes the numbers agree with each other when you multiply them all together. So this is just a constant. We don't have an explanation why this is 6.67 times 10 to the negative 11th, but that's the number we plug in to make the values work with one another, and that's what's called a fudge factor, probably not very formally in physics. So that's what G is. ME is the mass of the Earth. Think about that for a second. Is the mass of the Earth a constant value? Yes. For our purposes, the mass of the Earth in this problem is going to be constant. Is the mass of the Earth changing? Well, to be honest, it is a little bit very slowly as gases seep out of the Earth's atmosphere into space, especially helium gas and hydrogen gas are able to do that because they're so light. However, it's negligible for our purposes. So the mass of the Earth is going to be a constant. And then the distance away from the center of the Earth is a variable because we're going to be measuring, taking very precise gravity, acceleration due to gravity measurements at different distances away from the Earth. That's what we're going to be doing in this. Hey, interesting side effect of the linearization problem that we're working, we're going to be able to find what the mass of the Earth is. I'm not going to actually have that value as a given right at the beginning. We're going to see if we can use linearization to find the mass of the Earth. And oftentimes, this is what linearization does. We use it to find an unknown value that's one of the constants in the slope m. Okay, and that's what we're going to be doing here. We're going to see if we can figure out what the mass of the Earth is by pulling it out of the slope value that we're going to find. All right, so we're ready to move on. Let's see if we can coordinate values in our general linear equation to values in our actual equation. And the first value was the easy one. The y value in the slope-intercept form is just going to be acceleration due to gravity. Again, remember, that's our dependent variable. And what are we saying here? We're saying acceleration due to gravity depends on the radius, the distance you are away from the center of the Earth, okay? So I just mentioned what our independent variable is there. We'll get to that in a second. What's our slope going to be? So remember, slope values have to be constant values in the equation. Well, both g and me are constants. So our slope is just going to be g times the mass of the Earth. Now this looks a little weird because I'm grabbing the numerator in a fraction, but if you look at the operations that are being done on the slope there, it's just g times me. And then what am I left with? Well, I'm left with r squared as a denominator in a fraction, or another way to think about that is 1 over r squared. And that's what x is going to be, 1 divided by r squared. So I'm just going to include that relationship over to right here. This is noting that instead of plugging in the x value from y equals mx plus b, that x is actually going to be 1 divided by r squared. And then my slope value is going to be the constant g times the mass of the Earth. Now you'll notice that just like before, there is no value for a y-intercept here. So I'm just going to take that plus b out of the general equation. And then we're just going to note this is a proportional relationship that the linear relationship should pass through 0, 0 on the graph. And we're going to see if that actually happens by using that 5% rule. Okay, so now let's take a look at some actual data. These are data that are distances from the center of the Earth. So to measure these, we had to have launched some kind of instrumentation above the Earth's surface and measured exactly what acceleration due to gravity was at each of these distances from the center of the Earth, which are also a certain distance above the Earth's surface. And then if I were to look at those accelerations that were measured, I'm just going to note that 6.38 times 10 to the 6th must be a value that's at the Earth's surface, and then all of the other values are above the Earth's surface. I don't have any data points below the Earth's surface, but that makes sense because I can't get under the Earth's surface an appreciable amount and then take instrumentation with me to measure the acceleration due to gravity at that position. It's much more difficult to go down in this case than it would be to go up above the Earth's surface. Okay, so what am I going to graph here? Well, I'm not going to graph r versus a directly to get a line. If I did that, remember, a is my dependent variable, so it's going to be on the y-axis, and my radius is independent. That's the value that I'm using to compare the accelerations against. That's going to be on the x-axis. This is not a linear graph. Okay, so I can graph this, I can look at this relationship. I can recognize this is an inverse type relationship with an asymptote at 0. Okay, but and in fact, I can just look at the equation and note this is an inverse square relationship. But this is not linear. So how am I going to linearize this? Well, instead of graphing a against r, what if I graph a against 1 divided by r squared? So let's calculate those 1 divided by r squared values. I'm just going to put those over here. Notice that they look a lot different. They're much, much smaller numbers. My radii here in meters were very large numbers, and now I'm dividing 1 by those numbers squared. So I'm going to get very, very small values for this. And when I compare those to my accelerations, notice that my data set becomes very, very linear. And because I very carefully measured acceleration at each of these points, and I very precisely measured the distances from the center of the Earth, I'm able to get a very clearly linear data set from these values. Okay, and that's how we did it. We graphed A against 1 over r squared instead of just A against r. And now I can find the actual slope of this equation. What equation is this? Well, you can see in the equation that my slope is something like 3.99 times 10 to the 14th. Whenever you see e plus 14 in an Excel linear regression, you know that that's times 10 to the 14th. That's how it shows that. And that's times x, so that's my slope times x plus 0.0082. First of all, let's analyze that slope. So here I'm just going to pull out that slope value, and it must equal the gravitational constant g times the mass of the Earth. We know the gravitational constant g, and when we went into this, we said the mass of the Earth is going to be our unknown. Let's see if we can find the mass of the Earth from these given values, and we'll see how close we are to the actual value. So when I solve this, I rearrange mass of the Earth equals our slope divided by g. I'm just going to plug in that g value there, 6.67 times 10 to the negative 11th, and divide. I'm going to get a very large number, 5.98 times 10 to the 27th kilograms. And to 3 significant figures, the accepted value for the mass of the Earth is 5.97 times 10 to the 27th kilograms. So there's probably a little bit of measurement error in my data, but this is a very, very good agreeable value for the mass of the Earth. Now, let's use our 5% rule with our data and see if that 0.0082 is negligible. And I have to use it with my largest y-axis value. My largest y-axis value is 9.80 meters per second squared. So what is 5% of 9.8 meters per second squared? That value is 0.490. And I'm just going to compare, is 0.0082 less than 0.490? It absolutely is, so that I can change the linear equation to get rid of that term entirely, and I'm left with 3.99 times 10 to the 14th x as my proportional relationship. All right, so that was a inverse square linearization. Let's do another one. And for this one, we're going to use the period of a pendulum. The period of time for a complete back and forth pendulum swing. So this is how long it takes for a pendulum, which is just a mass at the end of a string, basically, or a mass at the end of something that can swing through the air. It depends on the length of the pendulum. What is that relationship going to be? Well, the linear relationship is going to be this, but our actual relationship is a little more complicated. The period of a pendulum is 2 pi, you get some constants there, right? Times the square root of the length of the pendulum divided by acceleration due to gravity. Now, it's kind of tough to work with an equation with a square root in it. It's possible to do, but it would be a little easier for us to work with this if instead we just squared both sides. And that means we have to square everything on the left. That's going to be easy, t squared. And everything on the right. Okay, so let's do that. And if I square everything on the right, 2 pi becomes 4, which is 2 squared. Pi squared, notice my pi is squared, still a constant because pi squared is a constant value, but I have to remember that that value is squared here. And then times L over G because we squared that square root out of the equation. So this is the actual equation that we're going to use. Now let's coordinate things in our general linear equation with things in this equation. So what is our dependent variable going to be? Well, we're going to say the period is dependent. Whoa, wait a second. I thought that we were always going to use time as an independent variable. Well, actually I said usually, not always. Sometimes it's going to make sense for time to be dependent. And in this case, the time it takes for a pendulum to go back and forth depends on the length of the pendulum. It really helps if you can state things in a sentence like that to make sense of what the independent and dependent variables are. So my dependent variable here is actually going to be time squared. And when you see a capital T, we refer to that time as a period, but it's still a period of time. So the period squared is going to be my dependent variable. This is already shaping out to be different than the other examples, because in the other examples, my y value in my slope-intercept form always coordinated to just a regular to the first power variable in my actual equation. In this case, the dependent variable is going to be the value we're going to manipulate in our data set. I'll show you that in just a bit. What is our slope going to be? What are the values that are constant here? Well, 4 is a constant, pi squared is a constant, and then g is just 9.8 meters per second squared, acceleration due to gravity. So these are going to be my constant values in this equation. My independent variable x is going to be the length of the pendulum. That's going to be the thing that I can change and manipulate, and then we're going to see how the period is affected when I manipulate the length of the pendulum. And just like before, we don't actually have an initial value for our dependent variable, so we're going to get rid of that plus b from the general linear equation, the slope-intercept form, and we're just going to be left with a proportional relationship once again. And this proportional relationship just means that if I have 0 length, I would expect to have a 0 period. So my graph, my linear graph, is going to pass through the point 0, 0. Now, let's think about what we can find with this one. In the previous problem, we were able to figure out the mass of the Earth by taking a bunch of precise acceleration due to gravity measurements above the Earth's surface. We had a value related to the slope that was unknown. In this case, we know all of the values related to the slope. 4 and pi squared are just constant values, and so is 9.80 meters per second squared. That's a measured constant, but it's a known constant. So we can actually calculate our slope right away. And what we're going to do is we're going to collect a bunch of data here, and we're going to compare that data's slope to the slope that we have from our equation. And we're going to see if, in fact, this equation holds up to real-world scrutiny. So that's what we're going to use this slope value for. 4.03 is what we expect our slope for our linearized equation to be. Let's see if it actually is that. Let's see if this actually works out. So here are the data I collected for the lengths of several different pendula that I measured. In this case, I measured 7 different pendula lengths. And then here are the associated periods, the time it took for the pendulum to go back and forth associated for each of these lengths. When I graph this, we're going to expect to see a nonlinear data set. And sure enough, this does not look linear to me. It looks like it's going to be some kind of maybe parabolic or square root. It's definitely not an inverse. Actually, when I look at this, though, I remember from my equation that I was expecting this to be a square root relationship. And yes, this absolutely looks like it could be a square root relationship starting at 0, or sort of like a sideways parabola, half of a sideways parabola. That's what this looks like to me. So in order to linearize this data set, I need to graph t squared against the length instead of just t. So let's go ahead and do that. I'm going to add in my t squared column. So these are just whatever the period values were from before, except I squared them. And when I graph those versus the length, you see that the plot looks much more linear than it did before. And let's just compare the slope value here of 4.06 compares very nicely to 4.03. There's a little bit of experimental error here. I noticed that my points aren't perfectly linear. They're just very, very close to linear. But that is an excellent slope agreement. So I'm going to take it. That does confirm that the equation that I've been using to compare the length of the pendulum to its period is a valid equation. It is what we expected it to be. Now, what about that plus 0.0477, our slope-intercept? Do we need to include that? Well, we need to take our largest y-axis value from our original data set, and that was the period values, and our largest value was 1.93. What is 5% of 1.93? It's 0.0965 seconds. And let's see how that compares to our slope-intercept equation. The y-intercept there is 0.0477. Ooh, it's less, not by a whole lot, but it is less than 5% of the largest y-axis value from our original data set. So we can, in fact, exclude that 0.0477 value, and now we have a proportional relationship between the period squared and the length of a pendulum. So now you know how we linearize nonlinear data sets. We're going to be doing it this year with 3 distinct shapes of graphs. Those are parabolic graphs, and remember those can be positive or negative parabolas, square root graphs, and inverse graphs, and that will include inverse and inverse squared. And you now know how to compare the actual equation to the general form for a linear equation, in this case the slope-intercept form for a linear equation. Find the values that coordinate to one another, and then use those values with your data set to linearize.